Intro to Inference. In this program, we'll learn how to use Z procedures to make inference for the population mean. We're going to look at examples of statistical testing, what's called a test of significance, or sometimes called an hypothesis test. We'll also use confidence intervals to make estimates about the population mean. It's important to note that when we use any kind of Z procedure for the mean, these are known as sigma known techniques. In other words, if we're not given that we know the population standard deviation sigma, we shouldn't use these methods. Our tool for calculating the results of our Z test can be found in the Unit 2 Excel tool. Let's look at an example. You fill containers of soda to 12 ounces. Overfilling or underfilling is a serious problem. Assume that sigma is 0.5 ounce. Use alpha equal to 0.05. Use both the sig test results and the confidence interval results. First, we would have to establish what are the correct null and alternative hypotheses. Because overfilling or underfilling presents a problem, we're interested in results that are either significantly greater than 12 or significantly less than 12. As a result, we would hypothesize 12 ounces as a null and consider the two-tailed alternative. Next, we would need to collect some sample evidence. Our sample evidence here is a sample of n equal to 25 containers. The average fill for the containers, or x bar, is equal to 12.25 ounces. So let's run that example using our Unit 2 Excel tool. So here we are at the Unit 2 Excel tool. And I'm going to go ahead and click on the Worksheet tab, Z-Test, and CI for confidence interval. First, I'm going to input in my green input cells some of the information that I was given. I was told that my sample information comes from a sample of 25, and that the sample was the sample mean was 12.25 ounces. So my random sample of 25 containers produced a sample mean of 12.25 ounces. I was given the population standard deviation sigma was 0.5 ounces. Now remember that all of these procedures that we're looking at now are sigma known procedures, so we need to be given that population standard deviation, or else we would use a different method that we'll learn later. Now, after we've input our sample information, we can come down here to the significance test. The only thing that we need to input additionally would be the value for our null hypothesis. In other words, we are assuming that mu equals what? And the example problem told us that we're supposed to be filling the containers to 12 ounces. So we're going to assume that mu equals 12 to see if our sample evidence gives us enough evidence to reject the null hypothesis, in which case we would need to make some adjustment to the fill levels, or if there's not enough difference, we're not going to reject the null hypothesis. In other words, the process is filling the containers just fine. In this case, if we assume a population mean of 12 ounces, our sample mean of 12.25 ends up 2.5 standard errors above 12. The probability of being at least that far above the mean would be 0.0062. For this particular case, we want the probability of being either 2.5 standard errors above 12, that would be overfilling, or The same distance, 2.5 standard errors below 12, which would be significant underfilling. So our one-tailed p-value of 0.0062 needs to be doubled in this case, overfilling or underfilling. So the p-value for my test here is 0.0124. We were instructed to use a significance level of 5%. How do we make a decision for our test? Well, we've obtained the correct p-value of 0.0124. The alpha value of 5% or 0.05 is given, and it represents the limit for making a decision to reject the null. Specifically, when the p-value for our test is less than alpha, which it is here, we reject the null hypothesis. So we're concluding that the sample mean is significantly greater than the test value of 12. In other words, the p-value is less than alpha, so we reject the null hypothesis that mu equals 12 ounces in favor of the two-tailed alternative, simply that mu is not equal to 12 ounces. Looking at the confidence interval, I am 95% confident that the population mean fill level is somewhere between 12.05 ounces and 12.45 ounces. This entire interval is greater than 12, which again supports my decision to reject the null hypothesis. In other words, I'm pretty sure, in fact I'm 95% confident, that the population mean fill level, as is, would end up somewhere in this range, 12.05 to 12.45 ounces. Let's look at a one-tailed example. The average age of employees at your company has been 40 years. You work for HR, and you wonder if the average age has increased significantly. Here, the correct null and alternative hypotheses are shown. We would first assume that the age has not changed. In other words, that mu is equal to 40, and we would make that our null hypothesis. We're really interested in that alternative, whether mu is significantly greater than 40. So this would be an upper tail test, because the only results that are significant for us would be sample means in the upper tail of our distribution. Next, we would have to collect our sample evidence. We're assuming a known population standard deviation equal to 5 years. Our sample evidence in this case comes from a sample n equal to 25 and produces a sample mean x bar equal to 42 years. We're going to use alpha equal to 5%. Now we're able to run the test. Now let's look at that example on our Excel tool. I've already input my sample information. I was given that the sample of employee ages is n equals 25. The sample mean age was given at 42. And the standard deviation of ages, in this case the population standard deviation sigma, is required, and that was given equal to 5. I wanted to know if it seems, based on my test result, that the average age of employees at our company is increasing. So we're testing 40. We're testing the null hypothesis that mu still equals 40. But we're using an alternative that mu is greater than 40. So what I'm trying to do is reject the null hypothesis that mu equals 40 in favor of an upper-tailed alternative. In other words, that mu is probably something significantly greater than 40. And in this case, that is in fact the case. 42, my sample mean, ends up being 2 full standard errors of the mean above 40. On a normal curve, being 2 standard errors above the mean is pretty far. In fact, the upper tailed p-value here is 0.0228. And that means that if in fact the population mean age of an employee was still 40, in other words, if the null hypothesis is true, we just got a sample mean that only occurs about 2.28% of the time at random, which is not very frequently. So we either got a really unlucky sample mean, one with a probability or a p-value less than alpha, or the null hypothesis is false. So it's probably a better bet, based on the very low p-value, it's probably a better bet that the null hypothesis is not true and it should be rejected. In this case, because the p-value is less than alpha, we do reject the null hypothesis. Our evidence for doing that is our sample mean is significantly, not just a little bit, but significantly greater than the test value of 40. So we reject the null. Our p-value is less than alpha, which allows us to reject the null and conclude that the population mean is probably something greater than 40. Now the test of significance can tell me that much. It can tell me reject the null in favor of the greater than alternative. But it can't tell me what the population mean probably is. After all, we used to think it was 40, and now we've just decided that it's no longer 40, it's something greater than 40. That all raises the question, how much greater than 40? Our confidence interval will tell me that. I am 95% confident that the population mean age is somewhere between 40.04 years and about 44 years. So I am pretty confident that the population mean age of an employee is greater than 40, and we could see that most of that interval is quite a bit greater than 40, although our lower limit is pretty close to 40 nonetheless. Now let's look at a case that produces a need for a lower tail test. Say, for example, an investment analyst states that his investments have at least an average return of 8%. We want to test if this statement is valid. Because he's guaranteeing or stating an average return of at least 8%, we have to at minimum use as a null hypothesis that mu is equal to 8%. But here we're not really concerned with any return on average that exceeds 8%, because that would be consistent with his statement. The only results that are significant for us in this test would be if the average return for all portfolios he manages is likely less than 8%. So we would set this up as a one-tail test and specifically a lower tail test. As always for Z procedures for the mean, we're going to assume that the population standard deviation is known and equal to 1.89%. The sample evidence is a sample of size 30 with an X-bar value of 7.75%. We're using alpha equal to 5%. Now we're ready to run the test. Now let's look at this final example on our Excel tool. The investment analyst promises or guarantees that he's going to deliver a return of at least 8%. Even though that language indicates 8% or more, the only important part of the null hypothesis for us is the equality. Okay, so the investment analyst guarantees at least 8%. But statistically, the only thing we care about is putting some value there. We have to have a hypothetical value for mu in order to calculate our z-score, or also known as our test statistic, and the corresponding p-value that goes with it. If we don't have a test value for mu, that is, that mu equals some hypothetical value like 8, or 12, or 40. If we don't have that value, we can't run the test. So our null hypothesis here would be that mu equals 8%. And our alternative would be that it is something significantly less than 8%. Okay, the only time the analyst would have a problem is if the results indicate that the return is significantly less than 8%. If the guarantee is 8% and we exceed 8%, that's not a significant result. The only time this would be a significant result is if we can challenge that claim and reject it statistically in favor of something worse, that is, something less than 8%. So our null is that mu is equal to 8%. And our alternative here would be that it is less than 8%. Our sample mean is 7.75%, which gives us an indication that the analyst was wrong, right? We say, well, the analyst promised 8% and your sample mean is 7.75%. Well, we can't be too hasty, because if the difference between the population mean, at least hypothetical population mean, and our sample mean can easily be explained as just random sampling error, then we're not going to reject the null hypothesis. In other words, we're going to conclude that as far as we know, the investment analyst can be correct. And that is the case. The sample mean of 7.75 would be only less than 1 standard error below 8. That happens almost 1 in 4 times at random. In other words, just the luck of the draw in my sampling process can explain this much difference from 8%, 1 in 4 times, just at random. So there's no way for us to distinguish between random sampling error and a significant result. Therefore, we have to conclude that the results of this test are inconclusive. In other words, the p-value is greater than 5%, so we do not reject the null. And you could see on our Excel tool that that statement about our sample evidence being significantly greater or significantly less than the test value, that's missing, because in fact, 7.75 is not significantly less than 8. So that's not there. Instead, we see the following conclusion. In this case, we would not reject the null hypothesis. The population mean may be close to 8%. In other words, we don't differ significantly. Moreover, the confidence interval should support that result. And here it does. I'm 95% confident that the population mean return is somewhere in the range 7.07 to 8.43. The guarantee of 8% is in that range. So it's like saying I'm 95% confident the investment analyst could be correct. Remember that Z procedures, either confidence intervals or significance tests for the population mean, should only be used if we're given that we can assume knowledge of the standard deviation sigma. If we do not know sigma, or at least can assume it, we should not use these procedures. This concludes the program Intro to Inference.